Hey, this is Robert Niney, your spray foam advisor, and this video is an excerpt from a recent training that I just completed.
Building science is one of my favorite subjects because it talks about heat transfer and thermodynamics, and ultimately building science is the study of building materials and how they work in our environment and how they work together to create systems. And that's an important concept because when we use a product like spray foam, and really it can be any building material. How many of you are doing stuff outside of the spray foam side of things? You have other parts of your business that are related to buildings. So a handful of you, half of you at least. Whenever you do something to the building, you change the way it works. Right? You're fundamentally changing the physics and the principles behind how that structure works. So it's important for you and your team to understand what you are doing to buildings, and that's what building science is all about. Whether we're talking about the building envelope, we're talking about the building envelope in terms of insulation and moving the building envelope and changing the design of the structure. We're talking about the HVAC system, right? If you change something in the building envelope, it could have an impact on the HVAC system. And we're going to talk about some of those components and some of the specifics behind manual J calculations and sizing and design of HVAC systems and how what you do affects the world of HVAC. It can affect indoor air quality. Right? You're going to have a situation where your structure's tighter, the building you worked on is tighter, and things are going to happen in those buildings that people didn't know about before, that they didn't expect before. And there's a whole field of study related to that, and it's a subset of building science called indoor air quality. The weather conditions during your application and after your application are going to be directly related to how that structure performs that you worked on, right? Overall, the building physics, the energy consumption, all of these are subsets and subcategories of this large terminology that we call building science. If you are a nerd like me, there's this website out there called buildingscience.com. That is an architecture and engineering firm, basically, and they write papers and they do reports on these types of concepts, on all of these types of concepts. And there's free information, there's old reports from 10, 15, 20 years old about spray foam insulation. So if you go in and you're looking for information on spray foam, if you're looking for a third-party document to justify some of the things that you are offering with your products, there's information from a third-party engineering service that they make free and they make it available to the industry. So you can go print the reports right off of their website for things like buildingscience.com, their patriarch, the guy that created this organization, his name is Joe Stebrook, and he is the father of the unvented attic. It's his brainchild is where this whole idea of the unvented attic that everyone touches today, he came up with this idea, and it started back in the late 80s, early 90s, and he was doing this in Phoenix and Las Vegas in dry climates. And he had ways of doing it without spray foam insulation, before spray foam really took off and came into the fold and exploded in this application. But he is the reason that that air impermeable insulation is required in this unvented attic application. And we'll talk about that as I get into those concepts. So obviously we're dealing with insulation, right? And what's insulation designed to do? What's it intended to do? It's intended to manage heat. But one thing that's important about these concepts is that there are three forms of heat transfer, three different ways that heat moves, right? Convection. Who knows what convection is? Anybody? Convection oven? What does that mean when your convection oven is working?
Circulating the air.
Circulating the air, right? So convection is heat transfer by air movement. So as air moves across something hot, that air carries heat with it. And that air is convection, it is creating a convection loop that is heating up that surrounding areas, right? What about conduction? Anybody know what conduction is? So heat transfer by touch. It's conducting, right? We know that metal conducts. A metal stud conducts heat faster than a wood stud. That's heat transfer through that material. That's through a solid material from point to point. So conduction. And then radiation, right? We're familiar with radiation, right? It's radiant waves. What's probably the number one or number two example in our lives of radiation?
Microwave.
Microwave, that's right, yeah. And then one that I think it's pretty unique that we all experience, especially here in Texas, when you get into your car, why is it so damn hot in the car when it might only be 98 or 100 degrees outside, but you feel like it's 110 or 115 in your car?
Solar.
That radiation, that solar radiation off of the windshield, right? That windshield, that glass, is superheated. It's hotter than the air outside. And so that radiation off of the windows is actually superheating that space inside the car, which is why if you allow air to pass through the car before you get in, the car will be cooler than it otherwise would be, because the ventilation of the outside air at, say, 100 degrees is cooling that air in there that was 115, and it's cooling it down. So it's still hot, it's still 100 degrees, but it's more comfortable than being in that 115 degree car, right? So we have all three of these effects happening all the time. In everything, everywhere there's a temperature difference from one location or one material to another, we have these three forms of heat transfer happening right here. So one of the examples I like to give is coffee, right? A coffee cup. If you have a coffee cup at home, most of the time it's ceramic. But that coffee cup has a handle on it because the conduction from the coffee through the ceramic will heat up the outside and make it hot, right? The air going over the top of the coffee is convecting. It has convection heat moving through it. And then if you put your hand close to the cup, to the ceramic, but not up against it, just close, then you have radiation. The heat radiating from that hot cup off to your cooler hand. And so that's, the coffee cup is a perfect example, right? And then we put coffee in a foam cup to go because it has a higher R value than the ceramic, which means that it addresses more conductive heat flow, right? So we talk about R value in the building industry, and what is R value?
Resistance to heat.
Resistance to heat flow, that's right. R value is resistance to heat flow. But what we don't often tell people is R value only measures one form of thermal transmission. Which one is it? Do we know? It only measures conduction, heat transfer by touch. So R value is the only metric that we really have in the building industry, but it does not tell us the entire story because it only measures one form of thermal transmission. It only measures conduction, heat transfer by touch.